All right, now we're going to look at those nuclei that who are at the bottom of the non-radioactive nuclei. The non-radioactive nuclei are in green, right? So they don't do any decay. But at the bottom right here, so at the bottom means there are too many protons or too little neutrons. All right, that's why it's unstable. Well, to become more stable, these nuclei will undergo a process, a decay that increase the number of neutrons. Does it make sense? Okay, so it increase the number of neutrons. There are three ways that this could happen. So first one, alpha emission. So release a helium nucleus. Okay, so increase the number of neutrons. Positron emission. So take one proton, so lower the number of proton and make more neutron. All right, and positron coming out. Electron capture, same thing. So take one electron from one s orbital, the closest one, combine with proton. So get rid of one proton and make more neutron, basically. All right, and when this happens, so we have less proton and more neutron. So the neutron and proton per proton ratio will increases. All right, because we have more neutron now. All right, same thing with the positron emission. So number of neutron increases. So they go to 1 to 1.11. And electron capture, same thing, same effect there. So 1.12 go to 1.20. Okay, so it's basically the question is if a nucleus is not stable, why is not stable? Too much neutron or too little neutron? Okay, too many neutrons, well, they will go the beta emission, lower the number of neutrons. If there are too little neutron, well, we have to make more neutron. So either take proton to make neutron or release helium. Okay, so that's an increased number of the neutron per proton ratio, basically. All right, let's try one problem together. Okay, so which type of nuclear decay is radioactive isotope thallium likely to undergo? Well, before we get into the question, let's do this first. So this graph, it gives you just like the what we plot earlier to see the neutron per proton ratio. Okay, so at the this belt right here is called belt of stability. This nuclei is just a part of hold on, go back here. That belt is just a part of the band of stability. The belt is just the green one right there. The green who are those nuclei who are stable enough and non-radioactive. Okay, all right. So these nuclei are non-radioactive. They have the proper neutron per proton ratio. For example, technetium, right? 9943 is a perfect proton neutron ratio. Okay, if we have technetium 108, so way too many neutrons. In this case, it will undergo the process that will get rid of neutron and make more proton. All right, and that process is the beta emission. Okay, so start with 1.51 neutron per proton ratio. After beta emission, we got to 1.45, so a bit more stable. So drop down to the belt of stability. Now, if we have technetium 7843, which is too little neutron, we don't have enough glue. Well, easy to make more glue, right? So we will take either take proton and make more neutron. So we have to increase the neutron per proton ratio. And there are three ways to do it. So we have positron emission, electron capture, and then the alpha emission. Either one works, like all this work. All right. So the question is, which type of nuclear decay is radioactive isotope what's TM called? Hold on. What's the TM called? I forgot. Thallium. Yep. Thallium 163 likely to undergo. Well, thallium 163, 69. So where's thallium 163? If you look at this graph, 69 proton right there, and about 90 something. So 163 minus 69, that's about 94, about 94 neutron. Okay. So if you plot right here, you're going to see that the thallium is right below a belt of stability. What does that mean? Well, too low neutron per proton ratio, right? Too low neutron per proton ratio. So this guy have to do whatever it takes to increase number of neutrons and reduce number of protons. And there are three ways to do it. There are three decays that this could happen. So we have alpha emission, we have positron emission, and then electron capture. right? If you do alpha emission, so thallium going to go to holmium, holmium 159. Positron emission, we give thallium to erbium 163, and they are so one from a neutron per proton ratio 136, and they go 137 or 140. Okay, so A and B works for thallium. That's how we think about it. Okay, all right, let's moving on.